Next up, we have Zengxiang, who is the Executive Vice President of Digital Research Institute, ENN Group China. He will be sharing with us the topic on collaborative learning ecosystem for industrial internet AI applications. Thank you. Yes.
Thanks for the introduction. Can you hear me?
Yes.
Okay, thanks. So it's my great honor to share the topic and give in this talk in this event. My topic is collaborative learning ecosystem for industry internet AI applications. I come from ENN Group in China. Okay. First, please give me a few minutes to introduce ENN Group briefly. 33 years ago, ENN was started as an urban gas provider. Now we are covering entire clean energy industry chain. We have branches in more than 250 cities in China, providing a natural gas service to about 25 million families and 200,000 companies. Besides the energy domain, ENN Group also has expanded its business to tourism, cultures, health, and high-quality lifestyles with 4 listed companies. And since 2014, ENN Group has started its digital transformations journey. On 2020, we have transferred our headquarters as a technology company, ENN-EW. We built a new platform for accelerating our digital and intelligent transformations across multiple industry domains. As one of the 3 research institutes under ENN Group, Digital Research Institute focus on the industry digitalizations and artificial intelligence technology innovations. We are under one national engineering laboratory. We have set up our collaborative intelligence lab on 2020. We have recently get the federal learning certificate from China Academic Information and Communication Technologies. Yeah, this actually is an official one. Yeah, we have set up multiple application deployments, including energy load forecasting and equipment precision maintenance, and also some safety inspections. I will introduce some of them in my talk later. So there are 3 parts in my sharing. First, I will introduce our collaborative learning technologies, and then I will share our industry internet application practice. And last but not least, I will share my opinions for the development trends in this domain. Okay. First, further learning is a new AI modeling paradigm. So traditionally, entities in industry have to upload their private data to some AI model service providers. They put the data in the centralized data center and build AI models and provide AI model service to different parties. So it have to sacrifice their data sovereignty to achieve their intelligence transparency. So, but further learning have they changed this because they enables all companies to train their models locally and doing the model applications in the cloud. So in this case, we can achieve the intelligent transformations without sacrificing the data sovereignty. Yeah, further learning becomes a very hot topic since it was coined on 2016. This was the latest survey conducted by Tsinghua University. So we have observed the new focus in Internet of Things, edge computing, blockchains, and especially in these few years for further learnings. And we can also find out these trends in the publications, numbers of publications. And according to the Gartner's hype cycle graph, we can also observe that the maturity becomes higher and higher. Maturity of federal learning becomes higher and higher due to the efforts of both industry and academics. Yeah, and then there are also a number of industry standards have been released in the last few years. We have also attempted some of these, and also there are some very successful projects and platforms in China and overseas. Yeah. So in China, regarding to the application in China, actually there are more adoptions in finance domains and e-commerce, e-governance. Yeah, but in US and EU, actually we have found out a lot of efforts in healthcare domains to build better learning models across a number of institutions according the country boundaries. Yeah. But actually, we have also observed new trends, especially for our industry internet. In China, actually, President Xi Jinping have emphasized the importance of real economic developments. Actually, they encourage the digital intelligent transformations. Yeah. So in August, our chairman Wang Yishuo have provided a definition of industry internet, which links the industry demands and supply sides through digital and intelligent technologies. Yeah, but the data flow across different companies is still the obstacle to apply our intelligence technologies. So our vision is that we can enable companies from different industry domains to build intelligent models together to pull the industry, to hold the entire industry forward. Yeah. But there are a lot of challenges when we apply the federal learnings in industry internet applications. First, the federal learning global model is very difficult to meet the intelligent needs of all participants due to the diversities in terms of the industry domains, company scales, and also their digital intelligence companies capacities. Yeah. And also, the federal learning training cost is also very, very high due to especially for large-scale models. So it hesitates the industry adoption because the ROI is also uncertain. Yeah, and what is worse, the federal learning still have some risk of private leakage. So it cannot remove the concerns for our businessmen's concerns on data or user privacy and also legal compliance. Yeah, the last but not least, fairness and trust is also very essential to encourage our industry company to join the federal learning ecosystems. So, due to these reasons and challenges, we have proposed to upgrade the federal learning to collaborative learning. So we established the collaborations. We established collaborations in the diverse and autonomous ecosystems by choosing the suitable participants and suitable data to meet the requirements of individual participants. And furthermore, besides the model aggregations, we also emphasize the business value sharing fairly across all the participants using an efficient incentive mechanisms. Yeah, so after a few trials in industry applications, we found out that the key to the collaboration success or the successful deployments in real-world applications, they have 4 factors. First is effectiveness, and then the second is the model effectiveness, and then is the efficiency and the privacy and fairness. And illustrates them further. First is about the effectiveness. Is we have to ensure the model generated by federated learning or collaborative learning performs well. This is very, very difficult, especially in industry internet, because the data heterogeneity is very, very common. Across the different industry companies. So it can be different forms. First is the classification labels distributions in CV applications, and then is the heterogeneous series patterns and trends. For example, our energy consumptions, the trends is totally different. And then last but not least is the statistical distributions. For example, our equipment IoT data. So to handle these data heterogeneity issues, we propose personalized collaborative learnings to build these solutions and during the end-to-end model generations. First, in the data pre-processing, we find out the data or measure the data similarity and do the clustering. And then for the model itself, when we do the model gathering, we make only aggregating a special part of the models instead of the entire model. And last but not least is the model aggregations. Recently, we have proposed to use the enforcement learning to make the decisions that the optimal weight of individual participants in their model aggregations to get a best model and to increase the convergence rate and efficiencies. Okay. And then the second one is the training cost. The training cost can be very high, and many industry applications qualify. For example, due to the model size increase, there's high communication overhead, and also in some trainings, the conversion rate is very, very slow. Last but not least is the scalability. If we increase the numbers of participants, the accuracy of the model will reduce dramatically. So we have proposed a number of approaches to improve to do the saving costs for the collaborative model training. First is the model compressions. We can plan the model according to the importance of individual blocks. And we also can do the quantizations to reduce the perimeter size. We can use knowledge distributions. Instead of the huge teacher's model, we use small students' model to do the model aggregation to save large amount of, can be up to 90% of the model aggregations overhead. Last but not least, a number of adaptation optimizations are used to speed up the convergence, model convergence. And it is also well known that the model updates, which leaving the participants may disclose some confidential information by some malicious attacks. So our platform also have applied secure multi-party computations, HE, differential privacy, and trust exclusion environments, various privacy-preserving technology to protect the model aggregations, to enable the secure model aggregations. Last but not least is the failures. To enable the failures, we have to measure the individual's contributions and then share the business value according to their contributions. So all these stages have to work closely with the AI models generation stages. I would like to share a 3-minute video to give a short introduction to our collaborative learning technologies.
In this decade, we have witnessed the rapid development of artificial intelligence technology driven by big data applications, novel algorithms, and increasing computational power. Industrial Internet of Things has dramatically speeded up digitalization transformation for various industry domains. However, the data owned by a single enterprise is relatively limited, and the cooperation among multiple enterprises should be beneficial to AI adoption. Due to the sensitivity of confidential data and the high cost of IoT data collection and governance, enterprises are paying more and more attention to data sovereignty, privacy protection, and return on value of data assets. As a result, data cannot flow smoothly among enterprises, forming isolated data islands, which have become a bottleneck for AI deployment in the industry. A new technology is desired to break the data islands, activate the ecosystem, and thus release the power of artificial intelligence. The collaborative learning technology developed by INU Digital Research Institute enables a number of enterprises to create AI models in a collaborative approach. Consequently, they could discover the insights behind the data and establish the entire industrial intelligent ecosystem without compromising data sovereignty and privacy. A collaborative learning platform has been developed based on IoT system and cloud-native technique stack, supporting many industrial application scenarios. In order to protect confidential information, participants of collaborative learning firmly keep their private data within sovereign territory, while co-creating high-quality AI models through moving and aggregating their locally trained models in a secure and privacy-preserving manner. Collaborative learning kernel modules are optimized to tackle data heterogeneity and system heterogeneity challenges, which are very common in industrial Internet of Things, and thus improve the model accuracy, enhance the model aggregation efficiency, and reduce the computational power and communication overhead. Through well-designed incentive mechanisms, participants' contributions to the AI model could be measured accurately, and the obtained business value would be shared accordingly. Therefore, participants are encouraged to contribute high-quality data to promote AI models and establish a sustainable industrial intelligent ecosystem together. The Digital Research Institute is committed to in-depth research and industrial practice of collaborative learning AI algorithms, kernel module optimization, privacy-preserving computing, and incentive mechanism. The novel technology is expected to promote mutual trust and cooperation across multiple enterprises from various industry domains, supporting INU to become an intelligent ecological operator, accelerating the development of the industrial Internet of Things, upgrading the industry intelligent means for the modern energy system, and the improvement of people's health and lifestyle.
Okay, thanks.
In this decade,
in summary, our collaborative learning platform continues to support both secured model applications across multiple industry participants, and also it adopts incentive mechanisms to enable the fair contributions, evaluations, and business value sharings. So we build our collaborative learning platform continuously to support various industry applications. So I would like to share 3 applications in this talk. First one is energy node forecasting, and then safety inspection using CV models, and last but not least is the equipment predictive maintenance. For the energy node forecasting is very important to a different application scenario in energy domain. And then the different kinds of time series forecasting models are very important, are the foundation of this service. But in your case, an individual urban gas company has the limited data features with insufficient time period accumulation. And then the collaborative learning is very, very important to leverage the data from different companies and build personalized AI models to handle the difference across different consumers and regions. As aforementioned, our collaborative learning platform supports model aggregations and incentive mechanisms. So it selects relevant data across all urban gas companies And then they build their models according for individual gas companies. And then because the collaborative learning model can increase the forecasting accuracies, so our gas companies can get some incremental profits in their supply chain organizations. And then this business value will be shared to the data contributors accordingly. Yeah, but when we apply the vanilla federated learnings in this domain, we find out that it can use all available data across urban gas companies. However, it performs even worse than solo models. That means that consumers use their own data only, because the data heterogeneity issues is very is very common in this large amount of consumers. Yeah. So in order to tackle this challenge, we have proposed cluster-driven personalized federated learnings by using the knowledge-based federated clustering and two-phase federated learning trainings, and also the attention-based model aggregation strategies. We can increase the forecasting accuracies significantly. And the result has been published in FL workshop and within the innovation world. This slide gives more details of our knowledge-based clustering algorithms. As you can see, the trends for different consumers is totally different. We have used different kinds of data processing, time series data processing method to do the decompositions and also similarity measurements, and then find out the best way to do the clusterings. And in addition, we also implement federated k-means mechanisms to do the clustering without seeing the private data. In two-phase personalized federated learnings, in phase 1, we can leverage all available data. And phase 2, we do the personalizations for individuals clusterings and considering the contributions for each consumers by measure the distance between the global model and their consumers' individual models. Yeah. The second application I would like to share is the safety inspection using CD algorithms. They have traditional 2D and also explain for some high defect detections, and also the SLUM, that is simultaneous location and mapping technologies, is 3D data with the locations and 3D locations and also the images. Okay, so we have support different kinds of application scenarios coverage the whole energy industry. So why collaborative learning is very important in this domain, in this application scenario? If we come from different persons' perspective, for example, managers are willing to disclose the data with potential hazards, and safety audience have limited their knowledge, and sometimes they make subjective judgments. From AI models, without sufficient data, the AI models generalities is for multiple tasks. And last but not least, the data acquisition is costly, and also the labeling is costly. So we use the collaborative learning to leverage the existing data across a numbers of gas companies in different cities. As mentioned, in CD algorithms, especially for hazard identifications as an example, the hazard data or labels are much more important to the model's trainings. Yeah, but also this data is very, very, very sparse. So as we can see, different companies, if you contribute more hazard data, we can find out that their contribution to the model is higher, and they can, using our incentive mechanism, they will receive more, the higher value sharing, business value sharings. Yeah. One of the most important things in incentive mechanisms is doing the contribution evaluation. So it's very popular to use Shapley value to measure the average of all marginal contributions in all possible conditions. This is also applicable to collaborative learnings across a number of participants. However, Shapley value calculations in collaborative learning is unaffordable because we have to do a huge numbers of model trainings to consider all possible correlations. And also we have to do a large numbers of model evaluations on the testing data set to evaluate the model's performance in different correlations. In order to reduce the cost, approximate Shapley values calculations algorithms have been proposed. So actually, we don't have to model. We don't have to generate models and evaluate the models for all possible correlations. And second one is we can, in the training, in the iteration training, if it doesn't change the model significantly, we don't need to measure the SB values as well. So based on the SOTAS method that was proposed by Yuhai's group GTG Shapley values, we have proposed new algorithms by considering the weighted truncations and also dynamic programmings. We can improve the efficiency significantly by 10 times. So the result has been published in FL AAAI 2020 workshop and winning the best applications paper award. Yeah, and what is more important is that how we can measure the contributions and also we can do the sharings, but how is it really effective in our real industry applications? So in order to do that, we have built an end-to-end solution for the household hazard identifications applications. We build up a standard validation data set based on the domain experts and our data scientists. And then use these standard validations, we can form this circle. Yeah, that is, we encourage, in this case, we can encourage the participant to contribute the scarce hazard data samples, which is very important to model accuracies. In order to investigate more complex incentive mechanisms and simulate the large-scale collaborative learning ecosystems, we have built simulators to consider different industry domains and different scenarios. Yeah. So, for example, our simulation can simulate different distributions across participants, and also we can simulate their behaviors and willingness to participate in in the ecosystems in different perspectives. And also we can measure how they contribute to the model and how this model accuracy can increase in different applications. And based on these simulations, we have done some. We can design or find out the optimal incentive curve through the simulations to increase the model accuracies and encourage the participants continuously, and we can have a sustainable ecosystem development. Yeah, and in this model, in this application, we have also adopted privacy preserving technologies to enable efficient secured model aggregations. We have proposed two schemes. One is the pairwise masking. The other is secret sharing secured aggregations. Yeah, so they have different kinds of pros and cons. The first one, they can only enable additive model aggregations, which might be sufficient for most FL cases, but it is very efficient. It don't introduce any other overhead. The second one, secret share, they can enable different kinds of aggregation algorithms. However, it introduces communication overhead. Also, it need to avoid the collusions between the aggregation models. Yeah. The last application I would like to share is the equipment predictive maintenance. In the equipment predictive maintenance is the most typical industry 4.0 applications. And also is very common in in energy domains. As you can see, we attach vibration sensors on different kinds of equipments to get the vibration sensors. And then this high frequent vibration sensor will do some feature extractions and gets a lot of numbers of features. And then based on our knowledge base, we can do the deductions. We can do the listening. And finally, we find out the faults of the different parts. Okay? But so it is very important. Equipment predictive maintenance is very important in our industry. However, it also faces some problems. The individual company is very difficult to build a high performance models because there are a number of equipment types and different operations conditions. And for individual company, we cannot connect sufficient types of failures and data samples. And also the labeling is need to done by professional guys is also very costly. Yeah. So we propose collaborative learning to enable a number of factories to build this model collaboratively to save the cost. Yeah. So first of all, we have used different kinds of data features and propose a deep learning model to detect the different types of faults simultaneously. And then in our federal learnings, we have do some enable personalized federal learning. We doing the clustering based on the knowledge feature extractions. And then we build the models for individual clusters. Yeah, this also has improved the effectiveness and performance increase. And then we have do something further, that is for hierarchical model aggregations. As you can see, the model was divided into two parts. First part is the lower layer. Lower layer is the common feature extraction blocks. So this is the share model. And then the second one is for the multitask classifications layers. This one is the private models. So when we do the model aggregations, only the common feature extraction blocks are aggregated in the federated learning manners, and the private models are aggregated for individual clusters only. So due to these efforts, as you can see, we have vanilla federated learning, clustering federated learning, personalized federated learning, and also the personalized federated learning with Shapley values. That is contribution-aware learning. So we can see that these methods could increase the accuracy continuously. Yeah. So especially for nodes with very low failure rate, which is very common in the industry. Okay. Besides that, we have also applied the knowledge distributions, as I introduced just now. of use the huge teachers model to do the aggregations, we use the student model to do the aggregations instead. In this case, we can save a lot of communication costs. Furthermore, the student model and the local model, they do the distillations in the bidirectional manner, so they can learn each other's. And then they can, by learning from the students, they have learned from other participants. Yeah. So this is a result. We can also say that it can save large amount of communication overhead, and also without sacrificing the accuracies. The second method is also to increase to reduce the communication overhead. We have divided the model into a number of blocks and measure the importance of individual blocks and only aggregate the models, aggregate the important blocks in the federal learnings. You can save a large amount of communication costs and also avoid overfittings. And this part of work was worked with NTU Enhanced Research Group. We have applied this work in our real-world use case across 2 factories, and then we can reduce large amount of communication traffic, and maintaining the model accuracies. Yeah. So this is very important actually in industry. Actually, our factories, the communications through the factories is the bandwidth is very limited and very costly. Yeah, so based on for this kind of these applications, we have do some real world deployments as mentioned just now. We have also do some demonstrations in our research lab. As you can see, there are multiple steps, and this is the main frame. You can see the equipments from different factories are divided into different groups. And then we train the models individually for each group, and we measure the accuracies and doing the contributions, sharings, and value sharings according to their contributions. Yeah. Okay. In last sessions of my talk, I would like to share my thinkings of the development trends in collaborative learnings. In my opinion, there are 3 ways pushing the collaborative learnings forward. First one is proof of concept. That is, they use the local trainings and global aggregation to protect the data privacy. And then the second one is for performance enhancement. Yeah, so this is we have to make the model effective to solve the data heterogeneity problems, and then we have to reduce the training costs and while providing the data privacy protections. Last but not least is the scalabilities for model trainings and performance. Now we are in a new stage. I hope the third wave will come. So in the future, we can apply the collaborative learning in industry layer deployments. So in this case, the system and platform interoperabilities will be very important. I also, what I mentioned, the incentive mechanisms and ecosystem development is also very important to build these models, build the intelligent models collaboratively. Yeah. So we have also observed there are some new AI technologies. For example, the lower tier deep learning network structures, self-supervised learnings, foundation model pre-trainings, and so on. And these new technologies will also change collaborative learnings. Yeah. So I'm thinking about the future of collaborative learning. It can accept an open ecosystems. In these open ecosystems, it can attract, it it can attract the participants for different kinds of industry companies. They have diverse compute data volumes and data quantities, and also the different computation resources. Yeah, and then for the federated learning training or collaborative learning training, we have to enable heterogeneous model fusions. It means because the participants have different data and different computing resources, we should allow them to use different sizes of models. And then these different sizes of models could fusion together to help each other together in this ecosystem to build a high quality AI models. And then the second one is the how to train a model. How to train models can be also more flexible. For example, we can do some asynchronous relay trainings. Yeah, instead of now we have to do the synchronize every iterations. It's also very costly and sometimes it's unacceptable in real world applications. And last but not least is that instead of training the data for individual customers, maybe we can use the foundation models way. We use the massive heterogeneous data to train the large-scale foundation model. And then use this foundation model to do some transfer learnings to individuals, clusters, individuals, consumers or clients. Yeah. And I would like to leverage a little bit more for the AI technologies. For example, the novel deep learning network structures. As we know, the transformer-based network has high achievements in the field of NLP and CV in these two or 3 years. So when we apply the transformer-based network, that is VIT, for example, in CV domain, for federated learnings, we have found out there are some huge advantages. For example, the performance and scalabilities. You can see that with the increased numbers of participants, the traditional model net decreased dramatically. However, VIT models in federated learnings can maintain the good performance. And then the second one is that we can handle the heterogeneous data much better, VIT models. And also VIT model can adapt to different domains, different categories of images. And last but not least, we can enable the cycling relay trainings. So it's much more flexible in the real world collaborations across different companies. And the second one is self-supervised learning. Self-supervised learning, as you know, the labeling and annotations will become the bottleneck of supervised learning in industry application deployments. Yeah, so there are contractive or masking learnings, the major technology for self-supervised learning. We have also applied some of them in CV and time series data. So we find out that they can extract rich representations. Then we use the foundation models pre-trainings they can support multiple downstream tasks. We can also handle the multimodal information fusions. Yeah. And then the third one is about the heterogeneous model fusion. As I mentioned, in the industry internet, the companies may have different numbers of data sets. The data volume can be different, and also their computation cost, their computation resources is also different. So in this case, we should allow the participants to select their models according to their situations. Now in this case, we have how to enable these participants to learn from each other. So we have this heterogeneous model fusion framework. Yeah, using different kinds of technologies. For example, we can do the speed learnings. So each client can only train a part of the model, and then they use the cloud resources to train the remaining one. We can also use the partial model. According to the capability of different clients, we divide the model, global model, into different parts for them to train individually. And also we allowed the centralized model is a huge one, and then the participants model is a small one. They enable a number of participants to teach the huge models. And the opposite way is that huge model can teach the individuals student models as well. Yeah, so this will enable participants with different capacities to join the parallel learning ecosystems easily. Yeah, the last point is the trustworthy parallel learnings, where I also find out that some of, I think the academic side is more highlight the malicious attacks in parallel learning. However, in new applications, actually there's a number of companies introduce the noise purposely. For example, this photo, there was the label. This label actually is notice the consumer, notice the family, your heater is not installed properly. So in our model, they will do the attention to this label. Because this label and the hazard is connected closely. So in our model, we'll put more attention on this label. Yeah. So this actually is a kind of shortcut learning due to the data noise. And also the other side is about the models, explainable AI or interpretable AI in the domains. This is also applied to collaborative learnings. Last part of that, I would like to share a little bit for the industry academia collaborations efforts we have done in these 2 years. First one is for the applications for smart, safe communities. We have used collaborative learning technologies to break the boundary or break the data silos across urban gas company, property company, water company, and also heating companies. Yeah, so we enable collaborative privacy computations to do some statistical analytics and rule-based reasoning, and also we're using the collaborative modeling to generate high-performance CV models to detect the potential hazards in the communities. So by leveraging the data across different companies, we can find out new business models. The second industry collaboration ecosystem is that we have leveraged the data across equipment manufacturers, equipment users, and IoT sensor manufacturers and university laboratories. They have different kinds of data. So we use their data to enable the predictive maintenance using our the heterogeneous model fusions framework, with our which was enabled by our collaborative learning platform. Yeah. So this will dramatically increase the predictive maintenance models accuracies, especially when the data is very sparse for individual companies. Yeah, so at the end, I would like to call for industry and academic collaborations in both industry internet applications and research collaborations. So, for example, our 3 kinds of applications mentioned today, actually we have attracted a number of industry in China, and also we have built research collaborations and joining different kinds of ecosystems and made contributions to the standards and also get some certificates from the official organizations. Yeah, and set up collaborations with multiple universities to build the collaborative learning platform collaboratively. Yeah. Yeah, that's all for my sharing. Thanks for your attention.